Good afternoon, everybody. This is Steve Wilson from the State Water Survey. Webinar today is Groundwater and Well Construction 101. We're with the private well class, and this program is sponsored, funded, and supported through the Rural Community Assistance Partnership, who's our partner on this private well program, and it's funded by US EPA. Thanks for joining us today, and we'll get started. So again, this is part of a national program, RCAP. If you're not familiar, I'll show you a couple slides in a minute. The Rural Community Assistance Partnership is a national nonprofit with 6 regional affiliates that work in all 50 states and the US territories. They provide technical assistance and guidance to small communities, both water and wastewater related, as well as private well owners all over the country. This webinar follows the materials we developed for the private well class, which if you haven't signed up for the private well class itself, this is not the class, this is a webinar that supports that material. It's a 10-lesson class that you sign up with an email address, and I'll talk more about that as well in a few minutes. But if this webinar is being recorded, we record every one of them. If you're interested in CEUs, either through Illinois LEHP program or through NEHA, you have to attend live to and participate in order to get credit through that. So you can go to our YouTube page and see all of our past webinars. There's a lot of good information there. As I'll explain a little bit, the questions every month are different, and so it's worth looking at those videos just for the questions at the end, because you'll learn a lot more about wells and some of those issues, because we, again, answer different questions depending on what we get asked every month. Speaking of questions, if you have a question and we don't answer it today, which we'll spend the second half of the webinar just doing that, you can also put your question in our question box or chat box on the GoToWebinar window. And Katie Buckley's here, she's following that, and we'll make a list of those. We'll pull them up at the end and go through them. We'll answer what we can and ask you to let us know if there's something we can't answer. We might ask you for your email so we can get back to you. But we will try to answer all the questions that we get today. As far as CEU guidelines or CE guidelines, NEHA has a 2-year credentialing cycle, so we offered this down the bottom left. The last time was in October, and before that it was the year before in December. And so if you have taken this particular lesson or class that on groundwater and wells, you can't get credit for it more than once during your credentialing cycle. The questions are different, but the base material is the same. And so just want to make everyone aware of that. If you are looking for CEs today, we can provide a certificate, a copy of the slide deck, and help complete the NEHA forms, and that's our email address to do that. Yeah, and so I'm Steve Wilson. I'm a groundwater hydrologist at the Water Survey. Katie Buckley's with me. She's our Water Resources Outreach Specialist. She'll be fielding the questions today. She will work with you on your CEU things afterward. And yeah, and Sally Dolan is also with us today. She's taking over our new hotline, which I'll talk about later, and started with us in August. Okay, first thing to do is a poll question. So, and it is important that you fill this out. One, it's a way we know you're here and paying attention when we go to look at providing continuing education credit. So Katie just opened the poll, and she'll keep that open for a minute or so. And it's, like everything else, we're grant funded. So one of the things we report is who are we reaching and what, where they're from and all those things. And so this poll question is just one way to get at some of those issues.
All right, we have 77% of attendees voted. We'll just give it a few more seconds here. 87%. Okay, I'm going to go ahead and close the poll, so get your answers in. All right, the poll is closed. I'll share the answers really quick. Wow, half of the attendees that responded to the poll are from a regulatory agency, which is great. We're happy to have you regardless of your role here today. All right, I'm going to close the poll, Steve, and then you should be good to go.
Thanks. Okay, so RCAP, I mentioned RCAP. There are 6 regional affiliates. You may know them from one of their names of their regional group. So like RCAC is the Western RCAP. We're in Illinois, so we're part of the Great Lakes Community Action Partnership region. So there's Illinois RCAP staff in Illinois. There's folks in Ohio. There's in every state that work for Great Lakes, but they operate in each of those states. So again, I mentioned many of them are water or wastewater actually licensed operators because they support small communities around the country, but they also have private well expertise. And each region has a lead that we work with who is a private well expert and answers a lot of questions. They can also work with you on things like if you want to put on a workshop in your local jurisdiction, or even do a workshop on Zoom or Teams or whatever. They can help you organize that. They can provide speakers for that, or even help advertise something you might already set up. Their role, like ours, is to support education and outreach to well owners, and they're funded through US EPA. It's all free to you as, if you're a county health department or local health district or whatever extension, we're glad to participate. I'd love to do that as well. I'd rather be in front of people and answering questions than sitting in my desk, that's for sure. One of the things that we developed a number of years ago was a well assessment. It's for springs as well, but it's a 6 or 7 page form that is really detailed. It takes several hours to go through. RCAP does these. They've done a ton of them around the country, and it's a way to, if a well owner's having a problem or an issue, or they just want to learn more about their well, it's a way to go through and talk about issues like, have they sampled? What kind of pipes do they have in their home? Is there anything near their well that might be a risk? Do they have a good well cap? Lots of questions. Do they have backflow devices on their spigots? Just everything that would generate interest and a question from a well owner then about, why do I need backflow prevention? So it's a really useful tool, and it was developed by a group of groundwater and private well experts from around the country. You can find that on our website under private well class/assessment. There's one for, we just developed one that's for on-site wastewater and septic systems too, and they can do both of those with a homeowner. And you just have to ask. It's like a sanitary survey if you're a health professional or with a health department that actually does sanitary surveys for your state compliance program. But it's really what it meant to be is a great way to educate a homeowner, a well owner about their specific situation. I've visited literally over 1,000 wells, and I mean, every one is a little bit different in some way. And so it's really unique. Most well owner situations, whether that's from the pipes in their home or, the well depth of the well, how it's constructed, what information is available, all that stuff. So it's a way to promote best practices and encourage communication. I always mention this, but one of the questions we get from homeowners or well owners is, well, I don't want to call my county health department because they might tell me I can't drink my water. I only know of one jurisdiction like that in the whole country. Most of the time, your local health district or county health department doesn't have the authority to condemn your well or tell you can't drink it. They may very well recommend it because they care about your health, but they will not, they can't force you to do that. And if you have any concerns, you can ask that question first. But they're a great resource for you as well. And I'd always like to mention that when I think about it. So they've done over, RCAP, the 6 regions have done over 3,800 of these assessments. Many times it's when there's a problem with a well, and the local or state health agency may ask RCAP to come out and do a more thorough look at the situation, and that's mainly because of resources. Folks have become aware that We have this program funded under US EPA where they may not have the staff to go out and deal with every well complaint or issue. And so it's been a good way for us to develop partnerships, and also gives our, especially our RCAP folks, by being out in the field and working with well owners every day, you learn a lot about wells and specific issues they have and unique situations that we run across fairly regularly, as it turns out. So I'm at the State Water Survey. Actually, all three of us are. And just a little bit about us. We're not real well known, just from the standpoint that, every state has a state geological survey, and most folks are familiar with that. Illinois also formed a state water survey back in 1895, really because of cholera and typhoid outbreaks and its relationship to water and safe water. And since then, we've grown into an agency that we house the state's well logs. We have a lab. We do a lot of work. When a well owner calls us in Illinois, we can provide them a lot of information from our files. We have records dating back to the 1800s on wells in Illinois. And we also help communities with water quality problems and do applied research related to drinking water and well water and groundwater issues. I talked about our history. As I've been here a long time, started going through some of our historical information and found all of these cool photos and glass plate slides of the water survey's activities dating back, like I said, almost the glass plates date back to as far as 1900. And so this is one of those where they're investigating the typhoid outbreak in Rockford, Illinois, and some cases, several places tied to milk. Everyone gets their milk from one shop, if you will, and that is usually a large tank where everybody's getting their milk out of a bucket, pouring it into their containers and taking it home. And so this was an investigation to see if the milk company might have been contributing to this. It's just pretty interesting stuff when you have a chance to go back and take a look at it. A lot of well drilling pictures. If you are a well driller or been around a drill rig much, I have the idea of welding all these spacers and riveting every 10-foot section with, literally, there's probably 75 or so rivets there. You can appreciate how the modern drill rig and modern technology has made things so much nicer. I imagine this well, I can't remember how deep it is. I want to say it's around 80 or 90 feet, but that's a painstaking way to put in a production well. And this is for the University of Illinois back in the day. I think it was in the 20s. An old drill rig, I just mentioned that. Weldon's a small town here in central Illinois. Things have certainly changed in the way that's done. These folks took a lot more risks then. Not that drilling is a safe profession today, but it's much safer than it used to be. So as a private well owner, here's the things that we really want to make sure people are clear about. What private wells aren't regulated. The Safe Drinking Water Act regulates community and public water supplies. Private wells are not. So you're on your own to make sure your water is safe to drink and your system's maintained so that you always have water pressure. Your water's safe to drink, all those things. And well water many times can be the best tasting, safest water in the world. But sometimes it can include things that are maybe odorless, colorless, and have no taste. And a good example is arsenic. It's naturally occurring in some groundwater, not everywhere for sure. But we have one aquifer here where there's several counties where there's a fair amount of arsenic. You would never know it from drinking it. So you need to test. That's the bottom line, to be sure. Just like a community water supply does, they have to test under the Safe Drinking Water Act. They have to, for compliance with that law, they test regularly every 3 months, and they have to make sure the water they're serving their customers is safe to drink. So I grew up on a well, but now I live in town, and so I pay $60 to $80 a month, which this used to say 40 to 50 on this slide, but I do have a teenage daughter, and so now that's a little more every month. And that's the cost spread out among all the residents that not only allows them to sample and have a licensed operator, but also whenever there's a main break or water lines need to be fixed, all that is part of that cost. And you need to think about it that way if you're a private well owner. You need to maintain your system. You need to make sure you're putting a little money away so that whenever you do have a pump fail, it's a mechanical device, eventually it will, or there's some other issue, you test and discover you have a contaminant and you need to add treatment, that you've got a way to do that. And you just need to be responsible and a good steward, both to protect your family and also the aquifer in some cases. So what we really hope to get out of our 10 lesson class and these webinars is really, this is kind of what we want everyone to learn, if you will, that you need to understand where your water's coming from. So you need to have a well log if it's available and understand what's on it. And we're going to go over that today. But you know, how deep it is doesn't necessarily matter in some cases, whether it's got a screen or not, whether the pump's down in the well, or if it's at the surface, all those things. You can find out from your state or local agencies a lot of times if there are any natural occurring contaminants. If someone calls us, I can tell them where we know there's arsenic in the aquifers and where there isn't. There's other areas of the state where there's different constituents. We have an area where there's salt water upwelling into the freshwater aquifers, you know, that's buried from 1,000 feet below land surface. So knowing those things and knowing who to contact, it's important for you to be a little inquisitive, be a good investigator, and find out if there's anything like that that could be a concern. Some things like iron is, you know, pretty ubiquitous in groundwater, and it's also, you know, it causes those red stains. It's not a health risk per se, but understanding those things may help you understand what you need to do if you want to avoid those things or red stains on your clothes in some cases when it's really high. It'll also help you learn which questions to ask when you have some knowledge about your well and that light bulb goes off. You'll be much better equipped to talk to a contractor or a plumber or your health department or your geological survey, whoever it may be, about issues related to your well. And then lastly, you know, sample your well. It's estimated that 2/3 of well owners have never sampled their well water, and that should say sample your well water, your drinking water. But it's necessary, and it's something that is simple to do. It does cost a little money, but it's important and it's part of the protection for your family's health. So a little bit about groundwater basics today. There are really two types of aquifers. There are sand and gravel aquifers, which that's what this is. You know, those are little sand grains, and it's porous. So if I have a jar of sand, like this square that's here, this box, the sand, if it's dry, about 30% of that space, if it's uniform sand, is actually air. So if it's full of water, there's 30% of that volume is actually water. And that's what porosity is. It's a measure of that space that's not actually the sand grains. And so if I have an aquifer that's all sand and gravel and it's uniform size and it's 100 feet thick, if it's full of water, I could take all the sand away and I'd still have 30 feet of water over that entire area. So these type of systems, especially sand and gravel areas, tend to be highly productive. You see along river bottoms all over the country where there's big sandy areas where they're growing vegetables and melons and all that stuff. Those folks can pump, you know, 10 or up to 2,000 gallons a minute from some of their wells for irrigation purposes, because the aquifer can sustain that kind of pumpage because there's so much water available. And so the other side of that is a fractured system, which is bedrock. Water doesn't flow through rock, it flows through the fractures and fissures in rock. So depending on the type of rock and how many fractures there are and how interconnected they are, that's going to determine how much water is available to a well that's finished down in a bedrock aquifer. And it can vary from an enormous amount. We have an area in Illinois where there's a lot of irrigation that is a bedrock aquifer because there's large fractures and they're full of water, to you know, out west, granite is not very porous. It doesn't have very many fractures, where you may, I know there's a person that lives on the western slope of the Rockies that contacted us. His well only pumps a half gallon a minute. That's all it'll sustain. And it's just because that's what's available. And it just depends on where you're at and what water might be available and what kind of geology you have under your land. So looking at this, and more holistically here on the top, we have unconsolidated material, which is sand and gravel, clay, silt, that's above bedrock. And in some of the country, bedrock is certainly at land surface, so that's your only option. But in river valleys or in the northern states where there may have been glaciation, like in most of Illinois, you also have these unconsolidated areas where, like in Champaign County where I live, it's about 300 feet to bedrock. And so it's all sand, silt, and clay. Above that, it's not consolidated hard like a rock, if you will. And so this is just some differences. You know, we have a lot of karst or caverns and limestone areas in southern Illinois, Indiana, Kentucky, Tennessee. And so those are good because, you know, those large caves were formed from water running through them. And so they store a lot of water, but they also cause sinkholes at the surface. And so things from the surface can get directly into the aquifer and contaminate it. So it's a kind of a double-edged sword in that respect. The other thing besides porosity is permeability. And those are the two terms that are probably most important for dictating how much water can flow to and be pulled out of a well. And so it really depends. Permeability is about how easy it is for water to flow through that material. You can think of it as a velocity. So like here it says for gravel, 300 feet per day, that's a speed, right? It's not quite that a velocity, but it's about, it's a measure of how easy it is for water to flow through the grains of sand or the gravel there. And the larger the material, the easier that is. So you can see on the left, we start with gravel, the largest particles up to 3,000 feet a day. If there's, you know, water flows based on pressure. Like if I pour water on a table and lift one end up, water is going to flow down that table because it's going to a lower pressure thing. Or an opposite way to look at it is if I have a juice box with a straw in it and I squeeze it, I increase the pressure inside, so water comes out the straw. That's very similar to the pressure in an aquifer. When you put a well in, that's the straw. The water level may come up above the top of the aquifer because there's pressure on the system causing that. So going back to this, as you get to smaller and smaller particles, silt and clay, they become, they still may hold a lot of water. Like a clay can still have a permeability, or I'm sorry, a porosity of 20 or 30%, but because the particles are so small and they're so odd shaped and water has to take such a traverse path through clay, it's considered an aquitard or an aquiclude. It doesn't really let water through it very fast. And we're looking at 1 foot in 10,000 years is the low end of that. And so it's really relatively impermeable in a lot of ways. Then on the bedrock side, which is the right, you have different kinds of rock that may have large fractures. So if they do, like limestone typically does, then water's flowing almost as fast as it would in a sand and gravel aquifer, just through those fissures though, and in fractures, not through the rock itself. And then going down further, shale is basically cemented clay. It's very impermeable, and you can see here on the low end, 1 foot in 100,000 years. And so when you hit a shale layer as you're drilling into bedrock, you're not going to get any water out of that, or any appreciable amount of water that would fill a well. You need to find a sandstone or a limestone or some other material or large fractures where there might be water storage. So that's kind of both ends of what we're dealing with in geology, and why a driller may have to go a certain distance, or it could be that, you know, you hit a sand and gravel, but it's only 3 foot thick. And so that's not necessarily going to provide enough water once you start pumping. And so you may go deeper to find a thicker unit or something in bedrock. And that's, you know, we're lucky in a lot of respects that a lot of folks have come before us. So there's records in most cases of where there might be water in a given location. And so you kind of have an idea just from looking at other well logs where you might need to drill and how deep, like if, you know, you're buying a new property in the country and building a house, that sort of thing. This is just another schematic to show the differences. I think of this like a horse tank. If you have a horse tank full of sand and gravel and you poured water evenly across the top, it's going to move through toward going down from gravity in some kind of wetting front like that shows. Whereas the other three pictures are all bedrock, different types. So dolomite's kind of like, it looks like bricks, and it's the fractures. That's how a lot of that is. And crystalline bedrock is granite. Those fractures are typically really small. A lot of times the porosity of granite is less than 1%. So there's just not a lot of places to get water. It's very hard and it doesn't fracture easily where some of these other types of bedrock do. And in the real world, you have multiple geologies. So you have sandstone and dolomite here. This is still very much a simplification. Typically, these layers are not level, they're not flat, they're angled one way or the other, just the way the continents were formed and everything else. And I am not a geologist, so that's all I'll say there. But you know, in some cases you might have a shale that you have to get through before you can get to any water, but below that there's a lot of sandstone and it's full of water, and there's a lot of things available. So it's just, you need to understand, again, if you have a well log, what unit you're in, and all those things. So this is from Iowa. We actually adapted this from a resource from the Iowa Department of Natural Resources, but it shows really well what it looks like in a northern landscape where you have glaciation. So until you get to that first level of bedrock that is the limestone above the glacial, below the glacial drift, all of that material above that was left by glaciers and or windblown sands or whatever it might be, but it sits on top of the bedrock. And in this case, there's a river. You're looking at a cross section, so that little dip that it's blue at the surface is a river running towards us, if you will. And so the really saturated unit that's more blue with a little well in it by the river is the sand and gravel that's typically around a river basin from when the glaciers melted and they deposited all that sand. And then the other material is mostly silt and clay and not necessarily an aquifer, but all those little bluer units that are in the upper part are just thin sand seams where you might be able to get a well and have enough water or not, but it shows you the water level in those. And then going down through bedrock, there's a huge confining layer that is the shale. And then below that you hit limestone and sandstone. And in this case, that's considered artesian because the water level in that deeper well comes up above into the shale. So there's pressure on that system causing water to come up the well above the top of the casing. So that also means that limestone and sandstone are completely saturated. Any pore space they have is full of water. And so that's it's a pretty good diagram of all that stuff. Another way to look at things is, you know, water is part of the hydrologic cycle. So the water that's in the ground today at one point was not. It moves sometimes really slowly depending on the geology, but you can see from this diagram, everything here runs to this river. So water's seeping into the ground in the recharge area that's up where the trees are. It gets down into the water table, and so below that it's all saturated. And then those flow lines are actually a particle of water and how it moves. Some of it ends up in the river within a few days, as it's years, decades, centuries, or if it makes its way in the right spot, all the way down to that really deep aquifer, it could be, you know, 1,000 years or more before it ever makes its way back to the surface. But, you know, like, especially when you're talking to kids, a great thing to say is, you know, the water you're drinking today, there's a finite amount of water on the earth. It may have been drank by a dinosaur. You know, it's always recycling. It's all, again, part of the hydrologic cycle. What doesn't run in the ground or what doesn't infiltrate in the ground runs off into a stream or river, eventually gets to the ocean, evaporates, and starts all over again. So as far as aquifers go, really your availability is dependent on the geology. And so when you don't have a really good geology for an aquifer, where there's enough water that if you put a well there, it's going to be able to pump at a steady rate and you'll always have water available. Sometimes you put in a dug or bored large diameter well. In the old days, you know, a lot of people who lived in rural areas hand dug their own well. It's uncemented brick lining. It may have been less than 20 feet deep, but it's getting water from the water table, not necessarily from an aquifer. And that's, the water table is where, even if it's not aquifer material, I mentioned that clay before, still has a porosity of 30% or can, it can be saturated. And so water can slowly seep into that well. And that's why you make it a large diameter well, because it creates a bunch of extra storage. And so that's dug or bored wells are typically where there's no real aquifer. Other than that, you have a drilled or driven well into sand and gravel, and by driven really mean a sand point. Some states don't allow those. They're actually not a good idea. If you have a sand point, you should reconsider. There's no real way to keep that safe from any kind of surface contamination. They're typically really shallow, but a sand and gravel aquifer, yeah. And then the third type, as we already mentioned, is consolidated bedrock, which depending on what you have, where you live, it could be sandstone, limestone, dolomite, a lot of choices there. And in some cases, like here in Champaign County, we have 2 sand and gravel aquifers at different depths, separated by clay. And then we also have bedrock. And no one drills into the bedrock because the sand and gravel aquifers are shallower and there's more water available and it's cheaper, right? You know, it's a lot cheaper to drill a well 100 feet than it is to drill one 300 feet. And so that's, you can find out those differences just by talking to someone at your state resource agency or your state geological survey. You can Google water well logs or geology of my state, and you'll find the right sources online that you can then contact and get information. So dug and bored wells, these are all examples of dug and bored wells. The one on the top left is an old hand dug well for that farm that's still in use. It's covered by 2x10s and pieces of tin. You know, it's just not safe. The reason those posts look like they do is because that's in a pasture with cattle, and the cattle use those for rubbing posts. But while they're there, they're also doing their business. That's seeping into the ground. This is a hand dug well, so it's you know, water can seep into this well from any depth, and I don't remember how deep it is now, but it's just, this is a good example of a lot of the really old wells, like the one I grew up on, actually. The other two are both also bored wells. They're large diameter. So the one on the right is where you, most of the time these are concrete tile, which like the tile that runs under the road for to let water through. Those are 4-foot sections. You just put them vertically and you set them on top of each other, and water can come in at each of those seams. So like if we say that the vertical piece of tile that's in the picture on the right is a foot above land surface, that means at 3 foot, there is a seam where 2 of those pieces of tile were set on each other. They're not cemented, water can seep in, and every 4 feet. And I'll show you a picture of that in a second. The third one down the bottom left is really like the one on the right, except that concrete pad is 10 feet below land surface, and there's a 6-inch hole in it, in this case, for them to run a pipe up to the surface. And I'll show you what those look like here. So the one on the left here is the one where the pipe comes out, where the concrete tile comes up to the surface. And you can see this shows most of the geology here is soil, and it's brown, so it's not got a lot of sand in it, but there may be a few sand lenses, and that's where the water's coming from. And so it seeps into that well slowly at each of those excuse me, each of the seams where the concrete tile comes together. And so there's a pitless unit on this. This is in Illinois. It's based on Illinois Co-op Extension, a diagram they have. But that's why the pitless unit on the picture on the left is 3 or 4 feet below land surface. And so that that's there to keep from anything freezing. The other option I mentioned is the one on the right, where you have just a pipe coming up to the surface that taps into that concrete pad. And that's really so that you can create less risk of anything close to the surface getting in the well. So here they put clean earth fill, or you can put concrete in the hole that you've bored, and that'll keep anything from the surface from getting down in there, if you will. And so those wells, the same amount of water, they're the same diagram. It's just 2 ways of constructing a bored well for that. So the next type is a sand and gravel well. I mentioned already how prolific they can be, how much water you can pump from them. They have a screen. So a well screen is very much like the screen on your door. The screen on your door keeps bugs out and lets the air in. A well screen keeps the sand out, but lets the water in. So when a well's being drilled, the screen, the distance between those woven pieces of steel is a slot size, and the slot size that a driller will use is based on the material he pulls up. They try to stay away from fine sand because it's easier for it to get through those slots. And typically you don't put a sand and gravel well right at the top of an aquifer, because the way the sand was deposited typically is the finest material is the last to fall out when water's running. And so the thicker, coarser material is lower in the aquifer. And so you'll drill down in quite a ways until you hit more medium sand or gravel before you would put a well screen. The difference, the thing about a well like this is that it's solid casing all the way to the screen. So if this were a 200-foot well, and the last 4 feet were the screen at the bottom, water can only get in this well from 196 to 200 feet below land surface. That's awesome from the standpoint of protecting from surface influences. As long as it's properly grouted, which, you drill a hole to put a well in, the hole's bigger than the size of the casing. That area that's left around, it's called the annulus, and you fill that with clay or cement grout, and that's meant to seal it so that surface stuff can't go down along the casing and contaminate your well or your aquifer that you're getting your water from. And so that's the thing to remember, though, when you have a sand and gravel well, water's only coming in at the screen. And so here's a typical log for an Illinois well log. That's what I have to show you today. But you can see down on the bottom right, it says earth materials pass through number 24, 2 feet of soil, then some clay, then clay down to 172, and then they hit gray sand. So in the end, they were 40 feet of sand down to 212 feet, from 172 to 212. They pumped it. If you look right above that, it says water from sand 172 to 212. The static water level was only 72 feet. So the water level came up into the clay, which means that's also artesian because it's under pressure. And it dropped to 140 feet when they pumped it at 60 gallons a minute for 2 hours. So doing that, they know, for instance, that they can pump it at 60 gallons a minute, which is way more than anybody's going to ever use in their home. But by pumping it that hard, they know what the water level is after 2 hours. If they put a normal size pump, or maybe even a little bigger than normal, a lot of times that might be 5 gallons per minute. In this case, if you look over on the left, the pump capacity is 15 gallons a minute, and they set it at 124 feet. And so they've decided that if you're only pumping at a fourth of the rate, there's no way you're going to get it that deep, and they're right. It won't. It's got too much water available to it. So, and then above number 22, it talks about what they used. They used PVC down to 208, and then they have a 4-foot stainless steel screen that's 12 slot size. So, and I think that's 1200ths is what that stands for. And so all the water's coming in to this well from 208 to 212 feet below land surface, well into the sand and gravel aquifer. So the other type of common well, probably more common, are bedrock wells. And again, water doesn't flow through rock, it flows through the cracks and fissures in the rock. And because of that, you can't have a solid casing all the way through it to a screen. You have to take advantage of the fact that rock is solid, and if you drill a hole through it, the hole stays open on its own, where it wouldn't in sand and gravel, it'd cave in. And so you only put casing so far into the rock, and then the rest of it, you leave it as an open hole. And if you look at this example, the larger fracture that has, the blue, where it's a wider fracture and it has water in it, that's below where there's casing. So that actually gets into the well bore, right? And so in this case, typically a well has casing in bedrock 10 to 20 feet into the rock, and then they seed it there so that the rest of the hole is open, and the pump is below the casing. It's down where it needs to be for the water level, or what for pumping, and it's the number of fractures that you hit kind of dictate how much water might be available. Because of that, it's possible when you drill a bedrock well that you only hit one fracture. And depending on how deep you are and where that fracture goes, the water you're getting into your well could come from a much further away than it likely would in a sand and gravel well. So that's a concern if bedrock's close to the surface, because there may be a place where water is directly getting from the surface into these fractures, some of those sorts of issues. And so it's good to know how much casing you have. It doesn't matter. I know there was a question like, my well's 500 or 600 feet deep. Why should I be worried? Well, I was at a well in New York State that was 600 feet deep, and it only had 12 feet of casing, which means anywhere from 12 feet to 600 feet, water could get in that well. And that's not protective of the surface, only having that much casing. So if you have a bedrock well, it's really important to know how deep it is to bedrock and how deep the casing goes. I think most states now require that casing at least be 50 feet, even if bedrock's right at land surface. And so that's it's just a very different type of construction. So here's another well log, and this one is a bedrock well. So you can see from number 18, this is an older one. The well logs have changed over time from the Illinois Department of Health, but they hit limestone at 189 feet. And then they hit shale and went 3 feet into shale and realized that it wasn't just some thin shale. So they stopped, and the water is actually coming from the bedrock, the limestone, from 189 to 257. When you look at the static water level, it's 130 feet, number 17. And then they pumped it at 25 gallons a minute for 2 hours, it dropped to 160. So they put a 12 horsepower or 12 gallon per minute pump on. It's over at number 5. And they set it at 160, knowing that pumping it at a lower rate, the water level was likely not to drop that low. One thing I will point out here, number 15, they put black steel from 179 to 199. And so the limestone started at 189. So they went 10 feet into the bedrock and then seeded 20 feet of casing that's steel. So it's you can crack a PVC casing if you don't know what you're doing when you try to seed it into bedrock. So, but steel's much more expensive. So they used 20 feet of steel, and then the rest was PVC to the surface. And that's just so they could seed it into the bedrock without having any problems with cracking the casing. Pretty interesting though. Number 12, there's a mistake on this log that the person who filled it out was probably in the shop back at the office, and they looked at the very bottom geologic unit, which was hard gray shale, and they assumed that's where the water was going to come from, because typically you finish in an aquifer, you don't finish in the shale like it did here. So this should have said water from limestone bedrock from 189 to 257. Yeah, in Illinois, well records are public information. I think they are in most states. And so you can get online today and find this if you're interested. So as far as water quality, what we're trying to do, there are a lot of issues, but it comes down to either public health protection for the folks drinking the water, or source water protection so that people don't contaminate the aquifer that we're using, and generally just water quality in general, whether that's surface water, groundwater, protecting, because one becomes the other, right? If you ever heard the term gaining or losing stretches of a stream or a river, the gaining reaches are where groundwater is going into the stream, losing reaches of the stream are where surface water is going back into a shallow aquifer connected to the river. So it all interacts, and it all matters. There are a lot of things that we hear about often, whatever's in the news, whether it be drought or flooding. The term non-regulated drinking water, private wells aren't technically not regulated. So some folks use that term. PFAS is a big issue today. Lead was, 6 or 7 years ago. I mean, it still is, but that's when it first became a hot topic, if you will. And all these things matter. And if you're an educator, whenever the next thing that comes in the news happens, that's an opportunity to reach out to well owners, because a lot of times that's when they get more interested, is whenever there's been something happen where there's a water quality issue, and people naturally are concerned, but in a normal day, it's out of sight, out of mind. There's always water. It's not something to worry about. So we have to take advantage of those things. But what it really comes down to, and what I've learned, is that the two biggest issues that really affect private well water and the drinking water quality are poor well construction. Here's 2 more dug wells, both brick lined, both of them not protective from bugs or snakes, or we found everything from, well, I'll show you in a minute, larger animals in wells, And then also a lot of well owners just assume because it's groundwater, it's safe. When I say lack of well owner knowledge and education, that was my dad. I grew up on a dug well. It was in a ravine where water would flow to it from the surface in a pasture. It was never safe. I didn't know that then. I grew up on it. I do know now. And it's a matter of, my dad always swore that our well water was better than city water because they put chemicals in city water, and that's can't be good for you. So chlorine is a good thing. If you have bacteria, I mean, it can cause an acute illness where that'll prevent that from happening. So one of the things that we talk a lot about is how to improve poor construction. A well is expensive. Depending on where you live, it can be anywhere from $8,000 to $10,000 in the Midwest in a rural area to over $50,000 or $75,000 in California or New Jersey. So it's not a thing to take lightly. But as well construction codes have changed, all the wells that were drilled using the past code are all grandfathered in. They don't have to meet it, which makes sense because there's so many. But we have a lot of old wells that are not safe, that are in pits or that are hand dug, and they're still in use. And so not only are they an opportunity for surface contamination because they're not protective from surface influences, but they're also a safety hazard. So here's two examples. The one on the left is from the Washington State Department of Ecology. They're actually the agency in Washington State that regulates well drilling and well construction. And they had a blog, and this is from over 10 years ago now, but on their blog, this picture they put up there, and this is a little well house. You can kind of tell that, but you can see how the rotting insulation is that gray stuff in the back, and there's a funnel for putting oil in the pump, and all that. And there was a piece of plywood over this, and the person who lived there stepped one time and it broke, and she fell and it killed her. It's just not a safe situation. I'm sure if anyone looked down that well, even when the plywood was there and put a camera down there, you're going to see a lot of things floating on the surface. And this is what's being pumped into their home for their drinking water. So, and this other well, Don Kelderman was down in Southern Illinois researching his family history and came across this old farmstead with an old well, and there was a dead goat in it. And that's, you could see the ribs, and it fell in there, and whoever owned that property put a piece of concrete tile and stuck it in so it sticks up about a foot above land surface. And this goat was loose, came by and saw that there's water there and fell in, and that was the end of it. And so you shouldn't have an open hole like that, right, on your property. And you need to make sure there's no way for things, even small critters, to get in your well. So what do? You should bring them up to code as much as you can. If it's in a pit, which I don't show an example of that, but before the advent of pitless adapters, people put their wells down in a pit because they had to be below the frost line in a cold climate during the winter, or the pipes would freeze. And so a pitless adapter takes care of that need. And so now you can have your well casing go all the way up to the surface and have a pitless in your well. And that would take care of that. And fill that up with clay grout. I mean, we've seen where in a well pit, someone's not paying attention with a tractor and they drive over it, and all of a sudden their tractor tire drops 4 foot down into this pit. It's damaged the top of their well. They can't get their tractor out. I mean, it's a safety hazard. Or where people have just walked, well, I'll show you another example. Just walked in their yard and there's an old well there and they didn't know about it. So you can talk to your well authority, your county, health department or extension, find out what they recommend in your area for what it would take to bring your well up to code if it's not. Same thing with abandoned wells. So if you think about every old farmstead in the country where there's a barn and someone buys that little 1 acre or 1.5 acre area and puts a new house on it, there's likely an old well there that no one knows about anymore. All the folks who did know have moved on or passed away. And because of all that, we know there are a lot of undocumented wells that are on file. In Illinois, we started requiring well logs in 1968, and in some states it was as late as 2000. A couple states don't require folks to to submit logs at all, or only if they're above a certain size. And so there are a lot of abandoned or unused wells out there that need to be properly abandoned and sealed. And so if you have one of those on your property and you know about it, it's worth getting that properly sealed. And most states in their well code have a regulated way of doing that. You have to follow their recommendations on what you fill it with, how often you have to have, a non-permeable material like clay or cement so that water can't move through it. But if you don't do that, somebody, whether they're supposed to be on your property or not, they fall and get hurt, or worse yet, it kills them. You could be liable. Or if someone's dumping things, we see that too a lot, where people throw things in this nice hole that's there and no one's going to see it again. If you contaminate an aquifer and it contaminates any of your neighbors and they can trace it back to you, you're going to be liable for that too, and it's just not worth it. We all need to be good stewards of those things. So here's two examples. Pictures again, these are both from Washington State, from their Department of Ecology. One, there's a horse that fell in and they're trying to get it out. And this other one, interesting, Sheldon, Washington man falls 45 feet into the well. He was just walking in his backyard and fell through into this well. They got him out and he walked away. He very, very fortunate. 45 feet, think about that. Was a scary trip down that 45 feet. And the newspaper clippings are all from the 90s. The third one is, if you're old enough, you remember when they carried it live on CNN. It took 18 hours, I think, to rescue this little girl. She was 18 months old and fell down a well, and it was just as wide as she was. So she got stuck, and they had, they carried it live overnight and everything else. And her name was Jessica McClure, and now she's a mother of 3. It's just, these things happen more than people realize. And it's always worth making sure any old wells or unused wells are filled in properly, and there's no chance of any of these things happening. So a little more geology, the difference between aquifers and aquatards, I kind of alluded to it. Aquifers are where there's enough water that you can put a well in and get enough water for your home supply, where an aquatard is a unit that prevents water from flowing. And so you wouldn't put a well there, and if you had water in your well where it seeped in slowly, you'd quickly pump it dry, and water can't get back into the well very quickly. So the definition, which folks argue about, it says a sufficient quantity to be of consequence as a source of supply. Well, that varies if it's for a home where you need 5 or 7 gallons a minute maybe, versus a small town where you might need 150 gallons a minute, versus a much larger community where you might, have 3 wells that all pump close to 1,000 gallons a minute. It's kind of arbitrary. It's about what your needs are. And the same thing, an aquatard is just the opposite. It's where there are inappreciable amounts of water available, or leakage into that aquifer or into that material. So, and so different people define it different ways. I think it's kind of silly. It's really about whether there's a good water supply there or not. And then they can either be confined or unconfined. So an unconfined aquifer is where it has a free surface, so it's not completely full. The best example of this would be a sandy area near a river. You may, if you're trying to dig even a post hole in one of those areas, 3 foot down there may be water. And so from that point on, no matter how thick that sand is, it's all saturated. But right where it becomes saturated and you have that free surface, that's an atmospheric pressure. So it's going to go up and down even when the weather changes and atmospheric pressure changes. That can cause water levels in a well that's in an unsaturated aquifer to change. And so a confined aquifer is one which has a cap on it, basically. And so it's usually like a shale or a till or a clay. And because of that, it's confined. Typically water, if you punch a hole in that and put a well in it, the water level will come up in the well above the top of the aquifer. It's up into that clay, or it's even further. And that's artesian. It means it's under pressure. And, you know, a lot of people think artesian means it's spitting out water, it's flowing. Well, that is also artesian, but it doesn't actually have to flow to be defined that way. And so here for an unconfined aquifer, it's all sand. It's just when you get to the water table, you know, it's saturated. So that's all the blue is where there's, it's an aquifer. If you have a confining layer, that red aquitard in the middle, then you have two separate aquifers, and depending on the water level in each, water may be slowly moving through the aquitard up or down. In this case, the unconfined aquifer at the surface, the water level in the well is higher than it is in the deeper confined aquifer. So that difference in pressure forces water to slowly move through that aquitard, but not at any rate that's appreciable for a well itself per se. It's the water's coming in this case from somewhere left or right to fill in, like when you pump this deeper well. So here we have a confined aquifer. So the little slash marks means it's a clay or bedrock or some other unit that doesn't allow it to flow. So the natural water level here is below the water table, but it's certainly also, and it's also below land surface. Well, that could be higher than the water table, which in case the pressure of the water in the deep aquifer is actually forcing water up through that aquitard into the water table. Again, water wants to be at a level pressure, equal pressure. So as long as there's a difference in water levels, it's going to flow in that direction. Or it can be flowing, which is a flowing artesian well. Here's another example to show it all at once. So in the grand scheme of things, this could be 200 miles wide. So at some point off to the right, the bedrock comes up to land surface, but near the stream, there's other material that's been left deposited by glaciers or from running water or whatever. So there's a confined aquifer that over on the far right, it's actually unconfined. But as you move down through the system to the left, there's a confining layer there, and it's at the level of, you know, there's pressure on that system pushing water to the left where it recharges on the right side. So the best way to look at it is the water levels, the dashed line. So the dashed line runs across the one that's straight for the artesian well, shows you the water level in the well based on the water level that's further right. And then as you go to the left, you're in a lower landscape and the top of your well is lower than what the natural water level would want to be. And so it flows. If you put more casing on this up above that level, then it wouldn't flow. It'd just be up in the well. It'd be a straight line all the way across. And then the shallower aquifer, the unconfined aquifer that's above the confining layer and connected to the stream, that's the water table. And you can see that dashed line where the water level is in that water table well. And that'll always be affected by the stream. And in this case, because usually the stream is a discharge point for these aquifers. And so that's why the water level is higher in the water table further to the right. And it's at the stream on the left side. And that's because it's discharging into the stream. And that's, again, part of the hydrologic cycle. So hopefully this makes sense. So it really depends on where you're at and how many options you have as far as water supply, but that's the difference in these two. Another way to look at this, this is DeKalb, Illinois is about 50 miles or so west of Chicago. So in this diagram, Lake Michigan and Chicago are on the right and DeKalb is on the left. And they're all pumping Elburn, Geneva, Elmwood, Bellwood. These are all communities in northeastern Illinois. They all have wells that pump from the St. Pete sandstone and the Ironton-Galesville sandstone. Those are just geologic names somebody named a long time ago. But these wells are, you know, as much as like the industrial site in Chicago is, it looks like it's about 1,700 feet deep. But what the red line is showing is the water level in those aquifers, and the wells are open to both. So the water is one water level in those wells that represents both of those aquifers. And you can see that on the far left, the red line's actually higher at the industrial site in Chicago than it is at Elmhurst, which means water's flowing. It looks like it's flowing up, but it's flowing because of lower pressure. toward the middle. And on the right side, or on the left side, it's also flowing right towards the middle because that's where water levels are lowest, and it's trying to fill in and become flat. Water wants to always be flat, right? That's like if you have a bathtub full of water, the water level in that is flat. It's the same everywhere. It's the same elevation. You have a plug, if it's right in the middle and you pull it, the water level drops most at the plug. That'd be your well pump. And then water's flowing towards it to try to fill it back in and be level again. If you plug it back up, it's a lower water level now in your tub, but it's all flat again. And that's what's happening here. There's more pumping going on between Geneva and Bellwood. And so that's causing, because there's other wells besides these, and that's causing a lower water level in the aquifer at those locations. And so water's trying to fill in and moving back towards that spot. And my point here was really that that could even mean that it looks like it's flowing uphill, like the two arrows on the right. It's not actually, it's flowing towards lower pressure, and that's how water moves. So as an example, simplified example here, the bottom picture, you're looking from the sky down at a well, and those are elevations. So at the well, it's 400 feet mean sea level. At the very edge, it's 460 mean sea level. So pumping this well has dropped the water level at the well 60 feet. And if you look at the picture on the top, that's if you slice through and we're looking at a cross section straight at it from in the ground. So this is the cone of depression. And so it's whenever you have a very uniform aquifer where the flow all through it's the same, it's uniform size, there's the same amount of water is available in every direction, it follows this radial flow. This is a perfect, would be a perfect situation that doesn't happen in real life. You know, there's differences in geology and there's boundaries and all these other things, but this is idealized how drawdown occurs in a well. And so when you start pumping this well, it's going to draw down most at the well, and everything's going to try to fill in from all around it, all 360 degrees. And so this is what water levels would look like in the bottom picture if you had an elevation at these different distances away from the well. So that's a typical cone of depression in a well. If you have more than one well that influence each other, then it affects things because water's coming in from further away on the left and right, but in between them, there's not as much water available because there's two wells pumping and they're both taking from the same, the water's trying to get to both and it can't, right? It's got to go to one or the other, so to speak. And so that makes the water level in between those wells much lower than it would be if only one well was pumping. And so that's kind of well interference, or can be. And then you also, if you're not far enough away from the edge where there may not be any water, in this case, the edge of aquifer that it's showing would be like a bedrock. The middle is a bedrock valley, and then you have the rock edges as it goes up, and then it pinches off the aquifer. That also doesn't allow as much water to come to the well because there's just not the volume there. And so that causes this elongated cone of depression that you see on the bottom, where there's more drawdown on the edge side than where there's more water available side. And so all of these things affect how much water can be pumped from a given well, or how much water might be available in a given aquifer, depending on the geology, where it's at, and then also, you know, the porosity and permeability of the aquifer itself that we talked about earlier. On the flip side, a river is like a constant source. You know, you're not going to pump enough to dry up a river. And yeah, I can't think of a case where that might happen. But because of that, the river is always providing water back to the aquifer as you pump it. And so that makes the cone of depression much smaller because the river is a constant source. It's always at an elevation of 445. You know, based on what a well can pump, the river, most rivers would have, you know, a huge number of times that volume of water available. And when there's no pumpage, is what you see on the right of the river on the bottom picture. That's the natural status of the water table. It's all that water, because it's 470 on the edge of the screen, and then towards the river it goes to 450 and 445. Water's naturally flowing slowly towards the river and discharging into it whenever there's no wells pumping at all. It's a natural system. So A number of states, like Illinois, have all their well logs online. We're a sister agency to our state geological survey, and so we work together on this. We house the well logs. They also have copies of well logs. They've developed this nice system. You can go in and search. These are all the blue dots are water wells, and I'm doing this near Champaign County, so I can zoom in and then click on a well, and it gives me some information. The API number is the identification number for the well that the GeoSurvey uses. Tells you a little bit of information, but then if I click on the blue number, I get a generated log. Their database, they actually put all the geology in, and so you can see some of this information. This isn't the log the driller filed. It's not like the other ones I showed you where that has the pump information and what they pumped it at and all that stuff. But in some cases, we've tried to link all these, and it's just, when there's resources to do that, it gets done. And so in this case, we've linked scanned actual log from the driller to their generated log. And if you click on the Get File button there, it comes up and shows you that actual well log. And yeah, so it's a nice system. A number of states have these available now. California, 10 years ago, you couldn't get a well log from a county unless you were the owner of the property. And now all their records are wide open and anybody can see them. And so, it's really the way it should be. This is an older well, 1959, says the date the well was completed. This form wasn't signed until 1968, which means somebody had an issue and the log wasn't in their file, so they filled one out for it. That's about when we started with those things. So that's our groundwater and wells stuff for today. I want to talk a little bit about our private well class program. Again, I mentioned it's 10 lessons, and the way it works, you sign up and it sends you a PDF as an attachment to an email once a week for 10 weeks. You're on your own to read it, self-paced, but it provides a lot more information about some of these topics and others than I could provide today. And it's on our website, privatewellclass.org. And we also have an email address and a dedicated phone line if you want to contact us. And people do. We have a lot of folks who call us and ask questions, and we try to help them either find someone locally if they're not in Illinois. If they're in Illinois, we've spent our careers helping well owners in Illinois, so that gives us an advantage there. So this is the front page. You just click on Take Our Free Class. You sign up with your email address, your first name, and what state you live in. That's what the drop down is. And that's really, again, we're funded through RCAP and US EPA. One of the things they want us to be able to show is that we are helping well owners in the entire country, not just Illinois or some other area. And so, we keep track of those statistics. We need your email address, obviously, so we can send you the lessons, but that's all it's used for. There's a Spanish version. If you're a provider and you live in an area where there's a lot of native Spanish speakers, you can go to this website and you can get to it from our regular site too. The entire lessons are there. Some of the videos are there, and it's all available. Again, this is all free. For each lesson, like the first lesson is called The Science of Groundwater. Some of the pictures we showed today, there's these other resources that are from other, a lot of times either extension or a university or a state agency on this topic. And it may be that the lesson we've written doesn't resonate with you well. One of these other sources hopefully will. They get used a lot. And there's specific information, like under lesson 2, the first thing there is the Michigan Flowing Well Handbook. So Michigan was losing 28 million gallons of groundwater a day to surface flow from flowing wells. And so they chose to regulate that. And now you have to seal that well in a way that it won't, water won't run out of it. And so there's a special cap at the top to keep that pressure in. And this handbook explains all that. And it's got a lot of great information about flowing wells. And I found it really fascinating, actually, because we do have some flowing wells in Illinois. Not very many, but we have a few places. Like this webinar, we record all of them. This is my water safe to drink from last year. It's one of a series of, I don't know, there's 4 or 5 webinars we try to do regularly, once, or at least once a year, if not twice or more. But in the end, you'll see today, the questions that we get asked are different. And so it's worth looking at these even if you, the other ones are on groundwater and well construction, for the questions that are in the back, so to speak. We do some specialty webinars like this one on financing and funding. It's probably the most common question we get is, hey, is there any help for me? I need to get a new well, my well collapsed or whatever might have happened. And unfortunately, there aren't a lot of places to go as a homeowner for help, but we try to go through what is available. A lot of times it's based on, your economic level. And so it's just, yeah, sometimes you can find other resources or maybe help for sampling or even for abandoning your well. All those sorts of things are covered in this. And then we did this webinar twice. The last time was in August of 2018. We brought in an expert from Virginia Tech who has worked with lead in homes with private wells, and she provided most of this webinar. But we also developed a lead page from this, and we have, it's what you need to know as a well owner about issues related to lead. Because, right now, all the talk in the paper and everything else is about states and the federal government providing resources for lead inventories and for communities to replace lead service lines. That says nothing about the pipes in your home. Even after they replace all the lead service lines in all the communities in the country, you may have, if your home is older and has lead pipes, you could still have lead issues. And so you need to understand that, whether you're a well owner or not, in all honesty. But this is for everyone who is on their own water supply and may have an older home that's at lead or copper with lead solder or galvanized piping. And there's a lot of them in the country. As I mentioned, we do have a web page that then you can look at for information here. If you have lead, the filters work really well at removing lead that are available. They're pretty reasonable. It's just privatewellclass.org/lead. And we also have a series of these training videos. We call them, they're 3 to 4 minutes long on one specific topic. What do I need to know about a shared private well? There's a lot of people who share their well with their neighbor or 2 or 3 neighbors, and that's all good until the pump fails and you need to spend $2,000 and all of a sudden somebody doesn't want to pay their share. And there's just a lot of issues if you're going to share a well and that you need to know about. And so we cover some of those things. What to do after a fire or a flood, what is a sand and gravel well versus a bedrock well, a quick description of those sorts of things. And pressure tanks. Our most popular video is about how does my pressure tank work. It's had well over 400,000 views since these were put up in 2016. And it tells us that there's not a lot of information out there about that, as well as that a lot of people have pressure issues. Either typically their pressure switch isn't set right or some other issue. We have a podcast. It's called drinkingwaterpodcast.org. We just started season 4, which there's 12 episodes per season. We interview people who are really players in the industry. Brian Swistock, the first one there, he's retired. He was with Penn State Extension. He's probably the most knowledgeable man I've ever met about private wells, and that's the truth. And I think most people would agree with that. Dr. Wolf is with Boston Children's Hospital, Harvard Medical School. He deals with cases of children where there are many times it's related to some issue with their drinking water. And so very interesting stuff. And so we try to, it's both on the rural community water supply side and on the private well side, but you can look through those. There's 36 episodes, or actually there should be 38 now. That we've had 2 for the season, about just different topics related to issues. It's kind of at the intersection of rural health and or public health and rural drinking water. So overall, this is the goal of our program. And we want to help well owners understand why their well is important, why they need to understand how it works so they can better be good stewards and protect themselves. And then again, protect themselves from risk from drinking water. It shouldn't be an issue. And it's not that some people are like, well, I'm just never going to buy a house with a private well. That's everyone's personal choice. But in most cases, there's no reason not to buy a home with a private well. You just have to know how to take care of it like everything else. It's being a good steward. and make it a responsibility that you want to take care of. So a couple things that are coming up. I mentioned Sally Dolan earlier. Sally was hired and does much more than that for us, but she is going to take over our private well hotline. So under our new contract with EPA, we're taking over their private well hotline. It'll be on their private well page, and it'll not only be a phone line where people can call in, but there'll be a website that's got this articles. It's called a knowledge base that's full of information, like the answers we put on here today. Some of that information will be similar, a little more detailed probably. But Sally's an EHP, environmental health professional, and so she's going to manage that and has put all the knowledge base together, and is eagerly awaiting, I think, or not, April 1st when this launches. And so we're pretty excited about it, just from the standpoint that it'll give us an opportunity to reach more people. There'll even be a chat bot feature on the website, so you can ask it for answers, and it'll give you answers based on the information we put in there. So it's all been vetted by us. Some other things, we're developing a lesson 11, working with the National On-Site Wastewater Recycling Association and RCAP on on-site wastewater, which, decentralized wastewater, on-site wastewater, it's, your septic system or a more advanced version of that for your wastewater treatment for a home system. And so that should be coming in the next probably 9 months to a year. We're also developing a website for on-site professionals called decentralizedwastewater.org. We hope that launches about the end of April. We're getting close. We have a few little technical issues, and we run another program called wateroperator.org, which has a huge database behind it in SQL, and this is integrated with that, and so we're dealing with some of those details on the back end with how to make this all work. But in the end, for professionals, it'll be a national calendar of all the training events. It'll be links to documents from all the different organizations and agencies that deal with decentralized wastewater, to provide it all in one place, like a clearinghouse. And that's what wateroperator.org is today. And we started wateroperator.org in 2009. And it's become quite a resource for the drinking water and centralized wastewater industry. So this kind of fits in between the private well and the public water side. So that, again, hopefully in a month or so, we'll have that out. So getting to our submitted questions, again, I remind you that Katie is watching the question box or the chat box that's on your GoToWebinar window. If you have questions, you can put them in there. And what I'm going to do now, though, is go through the questions that we've got. If you did just sign up in the last day or two, I probably did not answer any of those. And yeah, just because we had honestly plenty from the folks that had signed up since last week. So first one is about PFAS. Someone said info on PFAS. And so are they a concern? And PFAS chemicals are used in everything. We were just talking about collecting samples and how a homeowner is going to have a hard time collecting a water sample for PFAS, because even the shampoo they used the night before could have PFAS in it. And in the right situation, they could contaminate the water sample because of the shampoo they used the night before. That's how difficult this is. It's in everything. I guarantee you that anyone they test, the person themselves also has some of it in their body, but it's in the air, it's in our water, soil, clothes, you name it. Some of those we understand fairly well, and they've already created health limits or recommended limits. There's not a standard yet through the US EPA, but they've got recommended health information for some of them. But that's only like 6 or 8 of the, I think there's close to 1,000 actual PFAS chemicals. And so they're really working to try to understand that and how they break down, where they do, and how they all move. They're very different in some cases. There's long chain and short chain. I don't follow that closely, but they even can cause different health effects. So different ones are going to have to be treated differently, and they won't all be able to be evaluated the same way. So there's a ton of work going on. That's the good news. There's researchers I think in every university, there's folks working on PFAS issues, in some cases, many people working on PFAS issues. And so it's just going to take a while. And while, like I said, the EPA does have a decent understanding of some, there's others that we're just learning about. And so, yeah, I'd say here's what you need to know as a homeowner or well owner, that the encouraging news is that it can be treated. And testing to see if you have it is pretty expensive. But if you live near a known source, like a chemical plant or an airport, or where, if a house burned down very close to you where they use the firefighting foam, one of those things, then you might consider it. And you should ask someone who has expertise there whether you might be at risk. But I'd say in a typical rural area, you're not going to have a known source per se, and so it may not be as much of a risk. So, but there is ways to treat it. And I meant to give Katie these links before we started today, and I forgot to do that, so she can put them in the chat. But this will be available. You can just email us and request the PDF of all the slides. There's 3 ways that work. This is all based on this EPA document on PFAS drinking water treatment technologies, and the EPA treatability database. It lists a ton of information for every chemical and potential contaminant. It's more than the average person would really want to read, but there's certainly pieces of it that would probably be interesting. And so that's the good news. So it can be treated. And that's really all I'm going to say, just because, the information changes regularly as more work is being done and more testing is being done. And I think we'll be dealing with it in 15 or 20 years still, trying to figure out, it's used in everything, and it can't just go away at the drop of a hat. It's going to take a lot of time and a lot more understanding of how it works and which ones are, the most risk and all that. Well interference. So I'm hoping you address what it means when 2 wells are intertied, which I'm assuming this means well interference. And I covered that a little bit, but what happens really is that each well causes drawdown on its own. And when those 2 cones of depression overlap, then there's not as much water available to head back to the well for either one. So it causes, in between those 2, the water level to drop more. And where this would really become a problem is if you have 2 wells, they pump at different amounts, or the pumps are set at different places. So if this example is kind of idealized, and it shows screen right down, well screen all the way down to where the water level is. But let's say these wells are 200 feet deep, and one has a pump set at 100 feet and the other one has their pump set at 120 feet. Well, if it turns out this cone of depression for either one reaches 100 feet, the well that's pumped is at 100 feet is going to stop pumping because it's not going to have any water to pump anymore, right? The water level is going to drop below it. Whereas the one that's at 120 feet is going to be able to pump at a given rate until it either drops that low, or maybe it reaches a steady state where it doesn't ever drop below 120 feet. And so that's really where well interference could be an issue, is we have different uses, different depths. Like typically a community well, it's pumping hundreds of gallons a minute. It's going to go all the way to the bottom of the aquifer, and it's going to have instead of a 4-foot screen, it might have a 20 or 40-foot screen. And it's also, so it's also taking out a lot more water. Well, a house well that might be nearby maybe only have their pump, 10 feet into the aquifer, and then pumping a large well somewhere nearby may cause that pump to go dry. And hopefully in those cases, you'd be able to lower the pump and not, it won't impact your entire well. But in some cases it does that as well. So hopefully that answers your question. It's really about how much one draws down, how it might affect another. I know we see this in dry periods when there's a lot of irrigation, that some house wells might be affected and not have water. And so then, there's that usually leads to some kind of legal issue. So yeah. Why are some well pipes metal and others PVC? Well, so they're both common well casing types. And the first thing is, all states but 2 have well construction code that requires you to use certain types of material. Like if it's PVC, it has to be a certain thickness and a certain schedule, whatever it might be. The same for steel. And so other than that, typically it's driller preference, or sometimes it could be landowner preference. But the one thing is, PVC is not as strong as steel. That's for sure. And in the example we had, which I think I'll show again here, they used both, right? But that's because PVC is strong enough for most well applications. And if you have certain water quality or certain corrosiveness in your water, if it's got too high or too low of a pH, it can cause metal to corrode. And not that it's going to corrode so much that it wears a hole in the steel casing, but it's going to leach metals possibly into the water, which isn't good. The one thing that I can see where PVC in an extremely cold climate, like where there's permafrost, we're talking Canada or Alaska, it could become brittle enough that it wouldn't take much stress on a well casing sticking out of the ground to crack. And so I can see in those cases you might want to use steel. But otherwise, as I mentioned in our example before, they use both. So they use the steel casing to seat it in the rock because that requires a certain amount of torque and force to make sure that's sealed properly, and using a shoe or a drive shoe. And then they went ahead and used PVC above that because there won't be any stress per se, any kind of torque that might crack it or whatever. And that saved the customer probably a lot of money because steel is a lot more expensive. And this is that log, just to, number 15 is what I'm talking about. They used 5-inch PVC to 179 and then steel for the 20 feet, the last 20 feet, 10 feet into the bedrock. And so they could seat it there. Is there any benefit to putting a well house to cover, protect a well head and spigot? So this is a well house. It's the well I grew up on. It's got a dug well that is only 14 foot deep. It's kind of in a ravine. So water could run around the well house, actually even under in some cases. And so it would have really been a problem. The pump is on the surface. So in the winter, I live in central Illinois. We had some pretty harsh winters. We kept a propane tank down there so that when it got really cold and if our electricity failed, we could run a propane tank to keep all our pipes from freezing. And so the whole point here, I guess, is that it really depends on your situation. If your well is a normal drilled well and say it's PVC, but it's pretty close to your lane or your driveway, if there's a chance of a car or tractor or something hitting it, then it might be a good idea to have some sort of protection, whether it's a house or not. But if it's an older well, that like some of the dug wells we've shown today, where it's got a big piece of tin and 2x4s over it, or it's just got a handmade wooden thing that doesn't keep water out, I'd consider putting a well house around it. Just that way you can control what can get to the edge of the well casing or the top of the well. So it's really a matter of preference in a lot of cases, but I'd say in some cases like this one, it certainly matters. Not that it made our well any safer per se, but it kept from, stuff. It would have been a lot worse without that little building, I think. Who is the authority having jurisdiction? I've never heard of an HJ, just to be clear, of well construction in New York State and locality. So this really depends on your state. And I went ahead and answered this. It's really simple just to say New York Water Well Code in Google, and it came up with a lot of great information about the New York Department of Health and how the local health districts then enforce that code and work with drillers and everybody else. It's different in every state. It's DNR in Wisconsin. It's in Illinois, it's the Illinois Department of Health and our county health departments. 2 states, Pennsylvania, Alaska, they don't have well code, and they really don't have a certification program for drillers. So it's different there, and you'd need to look that up for sure. I know in Alaska, they have a work group. They're trying to actually get that stuff passed. In Pennsylvania, they tried for years to get their state legislature to create a program for regulating drillers and well construction code, and they can't get it passed, which is sad. But it's not on the folks in the state who care about water quality. It's on their state legislature. So yeah, and I showed this just because it is a question that if anyone has any questions, you just Google your state water well code and you're going to find the information you need. If my well is 500 to 600 feet deep, do I need to be concerned about what fertilizer and insecticide I use on the ground above? So there's a lot more to it than that, which I explained. If you have a 500-foot deep well, it's likely in bedrock. There is places where there might be sand that deep, but it's, you know, it does matter whether it's a bedrock well or sand and gravel well, as we talked about before. Sand and gravel well, the water's coming in at the screen, which is at the bottom. In that case, as long as the well is properly constructed and grouted, then it's very unlikely that you'd have any issue from anything you do at the surface. And, you know, a lot of folks live in these new subdivisions on the edge of town where maybe they don't have community water, but they have a well and it's butting up against a farm field. And I get that question all the time. You know, is this, how dangerous is this? It depends on how your well was constructed and where you're getting your water from, plain and simple. Same thing here. If it's the right geology and your well is properly constructed, then I would say there's really very little to no risk of those things affecting your well water. But if it turns out that you have that 600-foot well in New York that only has 12 feet of casing, then it's very risky. And it's very likely that anything from the surface is contaminating the shallow bedrock there. And because you put a big borehole in the ground that connects all these fractures, it's likely going to be in that and affect that. So, and you know, regardless, I grew up on a farm. It's still not a good idea to do things right next to your well. Just, you know, it's just for no other reason, it's bad karma to do that, I think. You need to try to protect the area around your well. What types of treatment systems do you recommend for methane removal? So there was probably 6 or 7 different questions about treatment for a specific thing today. And so what I've been doing, I'm going to do today, and you can look this up by just Googling MDH home water treatment. They put out a couple years ago this really awesome document that explains treatment in such a great way. It's easy to understand. It's broken down by treatment type and by constituent. It's a free download. It's something that I do. I believe every well owner should be aware of it. So I'm going to show that here. If you just Google again, MN home water treatment, this document will show up. And it talks about what you need to know, why, if you're going to have treatment, you should use one of these 3 certifiers. You should use equipment that's certified by NSF, the Gold Seal from Water Quality Association, or from Underwriters Labs that certify for water quality. And what that means is whoever developed this treatment device has given it to one of these 3 agencies and had them test it to meet a certain standard. So for lead, that means reducing lead down below 15 parts per billion. Or for arsenic, it's, you know, down to whatever level. And so they test it against water that is well above that. And if it meets their standards, then they put their seal on it. Now those companies have to pay for that. So when you look, if you go to a website where there is a whole bunch of treatment equipment options, if you just look for RO units for arsenic removal, you're going to see a list. If you sort it by price, you're going to have some that are in the $100 or $200 range. You're going to have some that are in the, you know, over $1,000 range. Somewhere in the middle, you know, around $500 or $600 is going to be a line where everything above that, that's cheaper, is not certified by one of these 3 agencies, and everything below it is. It's worth your money to always get a device that's been certified through one of these third-party certifiers. That's their job. They do everything right. UL, it's on light bulbs. I mean, every piece of equipment, every type of device, that's what they do. And it's worth always making sure that you certified equipment, just because that means there's a guarantee that it does what it says it'll do. And you're not, you know, buying some crazy treatment from someone who I'll mention alkaline water. Well, to someone with a pH, natural groundwater of a pH of 5, alkaline groundwater could be a pH of 7 or 7.5. Whereas in Illinois, most of our groundwater is already at 7.5 to 8. So it's it's a big word that gets people to think they need to do something different. You should find out why and make sure those things are certified. And I don't think you can get certified for an alkaline device, but I'm not 100% sure of that. Anyway, so methane is the bottom one of the 3 I marked here. There's really the best treatment for it's aeration and filtration. So what happens is methane's in the water and it's dissolved into the water down in the ground because of the pressure of the earth and the pressure on the aquifer itself. It keeps that methane in solution. But when you bring it up in your well or through your pump and it gets to atmospheric pressure, all of the methane releases. That's why if you have methane and you turn on your bathroom sink, it'll spurt and stuff, or you can light it, right? That's a common thing. So the way you get rid of it really is you do that somewhere before you bring it in the home or the first thing in treatment. So aeration is typically putting it into a tank that's got a vent and it's not full. So it's at atmospheric pressure. All the methane releases. It can vent out through a pipe that goes up to the top of your roof and discharges there. And so there's a lot of different types of ways to do that. If you're in an area that has methane, we have one here in Illinois. One of my cousins lived in that area and they used to they had a little pipe stuck to their well cap and they could light it and basically have a flame all the time on the top of their well, which, cool or not cool, it tells you how much methane they have in their water. And so depending on the compound you have, if it's arsenic, there's a lot of different ways to treat it. But then this document goes through all the different types of treatment. So aeration and filtration, it tells you what it might cost, if there's any maintenance costs, what are the pros, cons, blah, blah, blah. And then it tells you what it may remove depending on the type of device that you end up using. So it's pretty helpful. And this is just one page of many on the different treatment options that were listed on the page before. And so, yeah, there's a lot there. So carbon filters, hydrogen sulfide is a very common problem, that rotten egg smell. And so, yeah, there's a way to treat everything, just about. So, all right. Could you please cover pitless adapters and what they look like? So here's 2. One is a pitless unit and one is a pitless adapter. Basically what they do is they take your drop pipe that goes down to your pump and create this elbow down at 3 or 4 feet below land surface. And that allows you to run water into your home below the frost line, but then still extend your well casing up to the surface. And so there's, a driller who's going to install one of these will use one or the other and have a preference on what they're used to. But in the end, those things kind of unclip. And so you can pull the pitless out and then pull your well out if you need to service your pump or something like that. And then it all clicks back in place. And so it allows you to make that 90-degree turn to your house. Yeah, so before this, your well would stop right where this is, and that's 3 or 4 feet below land surface. And then you just have your pipe coming out of the top of your well, and but the whole thing would be down in a pit because you don't want it to freeze and have this water line freeze in the winter. A frozen pipe usually busts and it causes a big mess. So yeah, these are the common ways that's done. Okay, so water level below the pump. So I'm summarizing this because there was a lot more in this question. I didn't want to put it all on there. Basically, they have a 325-foot well that serves 2 homes, and the pump's at 150 feet. Sometimes the water level drops below that, and then they don't have any water. So they're asking if they should have a storage tank for when that might happen. And how would that work with 2 homes? So a lot of questions about, how to hook up 2 different tanks or 1 tank for 2 homes and all that. First thing is, you should lower the pump, right? You should, if the pump's at 150 feet, if you lower it even 50 feet, it sounds like it might solve your issue all the time. I can't believe, and maybe not, I don't know the specifics, but if your well's really at 325 foot deep, then is there a reason why you couldn't lower the pump? Have a contractor come out and put 50 more feet of pipe on, and or maybe, I mean, there's a lot of things it could be. It could be that your pump isn't strong enough if it goes deeper, or I mean, whatever, for 2 homes. But there are tons of issues with trying to use a storage tank, especially in this situation where you don't even know when you're going to use it, which means you'd almost have to have water in there all the time. And, you know, that water has to be treated. If it sits for any length of time, it's going to grow bacteria. If it's above ground and the sun's shining on it, it's going to be a problem. You need another pump just from your pressure, or from your tank, then to push water into your home and create that pressure. There's a lot of reasons not to do that. And so, yeah, it's, you know, people who have tanks now at their homes, it's because they regularly don't have water. Maybe it's a dug well and it goes dry every summer. So they have a way to hook up a large tank, and because some people certainly have to do that, but not intermittently when you're going to have, they go get water from town, right? A lot of communities have a place where you can buy bulk water when they need it. It's not something where you just store it. So, but yeah, it'd be interesting to see why you couldn't lower your pump further if you have that much left, so to speak, in your well. So we also got a number of comments, really. I just want to learn more about private wells. I'm just looking for foundational knowledge. I have no previous experience with private wells. My advice is to take our class. That's the best place to start. If you go back to our webpage, privatewellclass.org, you'll see right in the middle this little part of that page, take our free class, click on it, sign up. It's a lot of good information. And in total, all 10 lessons, I think it's about 80 pages, but that comes in, you know, 6 to 10 pages a week increments. And but it goes step by step through how water gets in your well, how contamination can get in your well, common problems people have, why you should test, where to find local information. I mean, it's a whole series geared towards, in the end, at least, you know, if you do have questions or problems, you'll be able to ask much better questions and have a better understanding of the terms and all of those things. So that's certainly what I would recommend. All right, so I'm going to go to the questions that you all might have asked. Let me find that. Is this showing up, Katie?
Yes, I can see it.
All right, great. So is a deeper well always a better well? No. It really depends on the situation, especially when you get into bedrock. You can have units that are high in some kind of metal or other constituent that's dangerous. I know Wisconsin has a deep bedrock layer that has arsenic at like 2,000 parts per billion. And so they've actually regulated that, I'm pretty sure it's Wisconsin, that if you drill a well that's going to go through that unit, it has to be cased all the way through it. You can't have an open hole in that bedrock unit, so that water, so nothing can get in it from there. And so you can either stop above it or you can go below it. But it's that one geology where there's just a ton of arsenic. And so it really depends. I would say in general, that's a fair statement. It's just not always true. So, and it depends, you know, again, it doesn't matter how deep it is. If you only have a little bit of casing, then that's really what dictates those things. So, yeah. A private well is downstream of a cow pasture. What can they do besides install a chlorinator to prevent contamination? Well, the first thing to do is to test and determine that you have contamination. Again, if the well's properly constructed and it's getting water from, you know, a unit that's more than 10 feet below land surface or 30 feet below land surface, it may very well be that none of that material is reaching the well water. It all depends on again, how the well's constructed and what the geology is there. And so as far as what kind of treatment, when people have, people have three choices. Let's say that you have a shallow well that you know is being affected by cattle. And this is really a pasture, not a feedlot, then it's less likely that it's going to be a strong source of contamination, like more confined type situation where there's a lot of cows. But if you do have that contamination and you know it from livestock, you have three choices. Go put in a different well, well two, I guess, or you can add treatment because you're not going to be able to do anything to prevent it getting in the ground. I guess my point is it's in the aquifer, if you will, or in the water supply in the ground. It's not because of your well not being safe. Then you really just you have two choices: drill a different well, or you can add treatment. And as far as treatment, you can use chlorine, like you mentioned, the chlorinator, or the other approach is to use UV, ultraviolet light. So there's a lot of UV systems now for homes, just because there's quite a market for it for springs, people who have a spring for their water supply. And so the deal with using a UV system is you have to manage it properly. One of those is that you have to have a filter in front of it so it takes out all the particulates. UV light works to kill bacteria and viruses and everything because it contacts it with a certain wavelength of light. If there's particulate in the way, it can't reach it. And so you have to filter the water first and make sure that there's nothing blocking that light. And then you run it through the UV system and it should kill or render inert any bacteria and viruses. So that's the other option. But they do sell those systems. You can find them anywhere. Yeah. How can I learn to read the well log I obtained? Well, if you're interested, you can scan it, or if it's a PDF already or some kind of file, you can email it to us and we'd be glad to go over with you. So just it's info@privatewellclass.org. And yeah, we'd be glad to go over. Every state, I showed you Illinois logs, they're actually pretty good. Some states have logs that need to collect different information or more information. So it depends on what's really there, and but it's certainly good to have that information. So yeah, we'd be glad to take a look at it. So all right, we're gonna get out just a little bit early today. So thank you everyone for attending, and yeah, have a great rest of your week.